It is often helpful to recognize special products of polynomials. We will consider special cases of binomial multiplication. We will state the formulas first and then show why each formula is correct, followed by examples. To compute the product of two multiplications by the FOIL method, we multiply a plus b times c plus d by multiplying the first two terms, a and c, plus the outer two terms, a and d, plus the inner two terms, bc, plus the last two terms, bd. FOIL is a shortcut. It stands for first, outer, inner, last. Next, we have perfect square trinomials. These are trinomials that are also perfect squares of binomials. A plus b squared can be computed by a squared plus twice ab plus b squared. Similarly, a minus b squared can be computed by a squared minus twice ab plus b squared. The last formula is called the difference of squares formula because the resulting product is a difference of perfect squares. To multiply a plus b times a minus b, we get a squared minus b squared. What's the difference between distributing and using the FOIL method for multiplying two binomials? Let's derive the FOIL formula to show that there is no difference between the two. We will make a table in which we give explicit justification for each step of our work. To multiply binomials, we use the distributive law to distribute the first binomial over the second one. Then we distribute again. Using the commutative law of addition on the inner two terms, we reorder AD plus BC. Thus, the product of the two binomials is exactly the sum of the products of the first terms, the outer terms, the inner terms, and the last term. Now let's consider some examples using the FOIL method. To multiply x plus 2 times x plus 7, we multiply the first two terms, the outer two terms, the inner two terms, and the last two terms. Then collecting like terms produces x squared plus 9x plus 14. Let's consider a product with a minus sign, x plus 3 times x minus 5. We still multiply the first two terms, the outer two terms, the inner two terms, and the last two terms. Collecting like terms produces x squared minus 2x minus 15. To multiply x minus 2 times x minus 7, we multiply the first two terms, the outer two terms, the inner two terms, and the last two terms. Then collecting like terms produces x squared minus 9x plus 14. Now let's make our problem a bit more involved. To multiply 2x minus 3 times 3x plus 5, we still multiply the first two terms. 2x times 3x is 6x squared, plus the outer two terms, 2x times 5 gives us 10x, plus the inner two terms, minus 3 times 3x is a minus 9x, plus the last two terms, minus 3 times 5 is a minus 15. Then we collect like terms to simplify to 6x squared plus x minus 15. To multiply x plus 4 times x plus 4, we can use the same process. Multiply the first two terms, the outer two, the inner two, and the last two terms. Then when we collect like terms, we get x squared plus 8x plus 16. Note that x plus 4 times x plus 4 is exactly x plus 4 squared, so we could have used the perfect square formulas. Before using the other special product formulas, let's see why they hold. First, consider a plus b squared. The definition of squared is a plus b times a plus b, which we can FOIL to get a squared plus ab plus ba plus b squared. Since ab equals ba, we can collect the like terms in the middle to get a squared plus 2ab plus b squared. Similarly, for a minus b squared, we get a minus b times a minus b, which we can multiply out to an a squared minus the outer ab minus the inner ba plus the last b squared. Collecting the like terms in the middle, we have a squared minus 2ab plus b squared. Also, a plus b times a minus b can be multiplied out. We have an a squared. The outer product is a minus ab, while the inner product is a plus ba, and the last is a minus b squared. Adding ab and minus ab gives us 0ab, and typically we don't write down terms with zero coefficients, so we have a squared minus b squared. We can also look at some examples. First, consider x plus 3 squared. Using the formula, we get the first term squared plus twice the product of the two terms plus the last term squared. This simplifies to x squared plus 6x plus 9. Alternately, we could compute the same product using the FOIL method. Squaring means the product of two identical factors. So then we multiply the first two terms, the outer two terms, the inner two terms, and the last two terms, and collect up the linear terms in the middle, x squared plus 6x plus 9. Let's compute x minus 5 squared using the perfect square formula. We get the first term, x squared, minus twice the product of the terms 5 and x, plus the last term squared, 5 squared. This simplifies to x squared minus 10x plus 25. To compute 3x minus 7 squared, you might find it easier to use the definition of squaring and the FOIL method. We multiply the first two terms, 3x times 3x, the outer two terms, 3x times minus 7, the inner terms, minus 7 times 3x, plus the last two terms, negative 7 times negative 7. Finally, we simplify to 9x squared minus 42x plus 49. In the product x minus 4 times x plus 4, we might recognize the special form for the difference of squares, or we can multiply using the FOIL method. If we multiply the first two terms, the outer two terms, the inner two terms, and the last two terms, we see that the plus 4x outer product and the minus 4x inner product give us a coefficient of 0x. So we simplify to x squared minus 16. The special product forms shown in this video are only somewhat helpful to multiply binomials. However, they turn out to be enormously useful in factoring trinomials, which is the topic of another upcoming video.